This is Math 140, day 15. We need to talk about some word problems involving linear functions and the average rate of change. So these are very easy word problems. They're about interpreting the numbers that you find in a slope-intercept equation. I'll give you two examples. Some construction workers are laying, let's say, fiber optic cable. And the length of cable on one particular line is, let's say, 1200 plus 600 x feet. When x is the number of days that they've been working. The number of days that they worked. So what can we say about this? Questions. What was the length of cable on day 0? That's when they started. And the answer is, you just plug in x is 0, it's the 1200. We're talking about feet. So that was already there when they started working. Question, how many feet are they laying per day? Answer, it's the 600. And this is in feet per day. Don't forget your units when you're doing an answer like this. For the equation itself, I don't want to see units, but for an answer to your boss, it's the appropriate thing to include units. So, remind you of anyone, this is a linear equation, a slope-intercept form, and the intercept, the y-intercept, that is at 1200. It's always your y value when the input value is 0. And down, what's that, 600? It's the slope. So they have a natural meaning, and people understand them, so that's why we love those two concepts so much. There's a lot more concepts in math which are harder for everyday citizens to understand, but those are not like that. One more example. The temperature. Of water at depth of d feet below the surface in, let's say, the North Sea, some spot in the North Sea, is 42 minus 0.5 d. Will not be a capital T for temperature. measuring temperature in degrees Fahrenheit, and D is the depth in feet. And then questions could be, what's the temperature on the surface? That's exactly like homework questions, by the way. That's why I'm asking these. The answer is 42. It's the y-intercept again. And question, how much does the temperature decrease with every foot in increased depth? Or how does the temperature change? That's the wording in the homework. For 1 foot of additional depth. Think a diver going down there, well, doing some repairs on an oil drilling platform or something. So the answer is, of course, negative 0.5. And oftentimes that's put in words with the word decrease. Degrees Fahrenheit per foot. And sometimes, like in Alex, they actually want you to use a minus sign. Or the change is minus 0.5 degrees Fahrenheit per foot. All of these examples are just really nice in that they illustrate beautifully how these formulas can make a lot of sense if you apply them where they are intended to be applied, but they have limitations. And Alex doesn't do much with that, of course, but whenever you apply that in the real world, you should sometimes spend a minute to remember that your instructor in Math 140 told you they have limitations. For once, if you plug in a negative answer for D, that means a negative depth. That can only mean going up in the air. And then chances are that this formula would totally be not valid. This is for water temperature below the surface. That would probably be a totally different formula. Next, very large depth. That would also definitely mean the formula is no longer valid, because at very large depth, I'm thinking when you get close to the seafloor, the warming from the inner crust, the inner molten core of the Earth warms up the ground down there. It's actually not that cold. So the temperature does not decrease and decrease forevermore. That would mean the water is frozen down there, actually, right? And it's not. I don't know how big that depth will have to be, but when it's really huge, so we're close to the sea floor, the formula would become invalid. And when your depth will be even bigger, then you're drilling through the seafloor and coming into the core of the Earth itself. It's not water temperature anymore. That totally would be a different physics environment formula would also be invalid. That will be under the seafloor. It's going to be a different formula, maybe a linear formula, but a different formula. We can pretty much bet on that. And it really helps to avoid embarrassment if you keep those limitations in mind. But it doesn't mean the formula is useless. No, far from it. For small depths, when you send that diver down, it makes total sense. But even then, even for the depths where it's supposed to be applied, the formula will not be exact, except by coincidence. Is slightly different spots in the ocean. Some of them may be more exposed to weather or cold currents. Then there's the seasons. So probably it makes sense to talk about the whole thing as an average over the entire year to begin with. But even if you take that average, there's going to be slight differences. And on any given day, anyway, it's not going to be the exact average. So a ton of limitations there for such a simple formula. And people still use them because they're useful and simple and just a rough eyeballing measure. Just keep those limitations in mind. Can we do the same exercise with the prior example? The cable. That formula obviously would not make sense when x is less than 0, because then the workers haven't started laying that cable and the 1200 were already there. It doesn't mean that a day earlier there was just 600. The 1200 was just their pre-existing line. Also, x less than -2, that would have meant a negative length of cable. Complete nonsense. Okay, so even more glaringly obvious that this formula is limited. And the lesson is, when you specify domains for a function, that is what people have in mind, that a formula in a real world problem only is applicable for a limited interval of input values. And a lot of insider knowledge can go into specifying such a domain. Domains can take care of some of these issues. That is the word problem part. One more thing, the average rate of change of a function. I'll abbreviate this as AROC. It's always of a function. and it's always between 2 points. And when we say points, oftentimes they just give you values for the input variable. So let's say x is x1 and x is x2. And then if you know that function, you can figure out your y1 and y2, or your unpaid intern can figure that out. But the important point is to keep track of the input variable. So what is that average rate of change? It is oftentimes called m, f of x2 minus f of x1 divided by x2 minus x1. Remind you of anyone? It's the slope. Slope of what? Slope of a straight line, yes, but what straight line? Of the straight line through points, and we've just done this about straight lines. x1 comma f of x1 and x2 comma f of x2, which are 2 points on the graph of the function. One example, f of x, also known as y, is x squared, and x1 is 1, and x2 is 5. What's that average rate of change? So our denominator is 5 minus 1. Our numerator is 5 squared minus 1 squared. And that is 25 minus 1 divided by 5 minus 1. 24 divided by 4 is 6. In terms of graphics, the graph of my function x squared looks like this. I need to scale this so it actually fits. X is 1, and it's 1. And x is 5, it's 25. I'm choosing very different scales on the x and the y axis. I also know there's a mirror image there. I'll make a nice graph. X is 0 gives me y is 0. And, well, it's supposed to look like this. And the average rate of change is the slope of the line through those 2 points on the graph. And we just calculated it. It's 6. So what? One thing that it tells you is, like we had in the word problems, when that slope is positive, or the average rate of change is positive, it means your function went up. It's increasing from this first x value to the second. And when the average rate of change is negative, or slope is negative, it's going down. And when the slope is 0, it's horizontal. Seen that as well in the first video. That's it for today. More examples in lecture.